How's everybody doing? What we're going to do right now is we're going to take a look at chapter 2.1, transformation of quadratic functions specifically. We did transformations in unit 1 of some lines. Now we're going to take a look at this with quadratic functions. Chapter 1, you learned transformation of quadratic functions, so you should have a good amount of knowledge in this section. We'll be adding in some application problems for quadratic functions here in a minute. Describe the transformation from f of x equals x squared and graph the function. So what we're doing here, as you know, hopefully from unit 1, we are going to shift this right 2 units. We are going to shift this up 3 units. Your vertex is going to be at 2, 3, and your line of symmetry, or axis of symmetry, means the same thing, is going to be at x equals 2. So what I like to do, right away I'm going to put in a dotted line right here at x equals 2. That tells me where the vertex goes. I'm going to go over 2 and up 3. So 1, 2, 1, 2, 3. And I put a dot right there. Again, that dot represents the vertex. Go to left and right 1, go up 1. Go to left 2, go up 4. 1, 2, 3, 4. And then what you can do is just go ahead and connect those dots with a nice smooth quadratic function or parabola. On number 2, let's take a look at the vertex. We're going to go left 1, up 4. Now what we have here are 2 things. We have a flip over the x-axis, and it's going to be a stretch or shrink of 1/2. So vertical shrink, 1/2, flip over x. And we do know, again, the vertex is right here. That's at 1, 4, negative 1, 4, sorry. And our line of symmetry is x equals negative 1. Again, the first thing I do is I go ahead and put in a vertical dotted line right here at x equals negative 1. I'm going to plot this point negative 1, 4. 1, 1, 2, 3, 4. That's my vertex. Now it's going to go down half as fast. So if I go to the right one, I only go down 1/2. Go to the left one, I only go down 1/2. If I go to the left one or right 2, I only go down 2. Here's our third one. Negative sign tells me it's going to be upside down. So flip over the x. The 3 here tells me I have a horizontal shrink. Of 1/3. Vertex is moved up 5. So my vertex is going to be at 0, 5. Line of symmetry is x equals 0. So the first thing I'm going to do is just go ahead and put my dotted line right here on the y-axis. So that's the same thing as x equals 0. Now the other thing I'm going to do is I'm going to change my scale a little bit just so it looks easier to read. So this is going to be 1/3. This is 1, negative 1/3, negative 1. Vertex is at 0, 5. So right here's my vertex. So with my scale, I go to the right 1, left 1, which is really left and right 1/3. And I'm going to go down 1. My next point is going to be here and here. And again, this is just based on my scale. On the back, we're going to take a look at some applications. Actually, not right away, but we will in a minute. Write a rule for f described by the transformation of f and identify the vertex of g. So you have f of x equals x squared plus 2. You have a vertical shrink of a half, followed by translation right 1 up 4. So you have a vertical translation of a half. So that means I'm going to take 1/2 times x squared plus 2, which is 1/2 x squared plus 1. Now I'm going to put in my translations. So g of x equals 1/2 x. If I go right, that means in the parentheses I have to subtract 1. And if I go up, I just add the 4. Number 5, f of x equals 4x squared plus 3. Horizontal stretch by 4 and a reflection over the y-axis, followed by a translation left 2. So I have a horizontal stretch of 4, which means I need to multiply it by the reciprocal. So it's really going to be 1/4 x squared. Now it says it's reflected over the y-axis, so I'm going to make that a negative 1/4 plus 3. So this is going to equal negative x squared plus 3. Now g of x, followed by translation left 2. So you're going to have a negative x plus 2 squared plus 3. Okay, I need to come back to this one right here. I made a slight mistake. So what this equals inside the parentheses, you're going to have 4 times 1/16 x squared plus 3, which is 1/4 x squared plus 3. Now we're going to deal with the left 2. So g of x equals 1/4 x plus 2 squared on all that plus 3. Number 6. The height h in feet of a water balloon is modeled by the following, where x is a horizontal distance in feet from the launch pad. The launch pad is moved up so the water balloon will land exactly 9 feet away from the pad. Write a function that will model the new path of the balloon. If I were to graph this function right here, what I find is that this is what my water balloon is going to look like. So what I'm going to do is I'm going to put that equation in my calculator. Plus 24x plus 11. Now what I'm going to do is go to my table, so I hit second graph. Now notice it says 9 feet away. At 9 feet away, this is negative 16, right? So this point right here is 9 comma negative 16. But what I want this to do is I want this to land on the ground right there. So what I have to do, my new equation is going to be h of x equals negative 13 or 3x squared plus 24x plus, now I take this 16 and I have to add it to the 11. It's like moving it to the other side. So what you have here is negative 16 equals negative 3x squared plus 24x plus 11. Now add the 16 to both sides. And this is when height is 0. Number 7. If an object is propelled straight upward from Earth at initial velocity 80 feet per second, its height after t seconds is given by the function h of t equals negative 16t squared plus 80t. T is the time in seconds after the object is propelled, and h is the object's height in feet. How many seconds after the object is propelled does it hit the ground? So that's what you're looking at right there. If I go back to my calculator, I can put in negative 16x squared plus 80t, or 80x. Then I go to my table, and I want to know when h is 0, what is x or t? 5. So this ordered pair right here is 5, 0. Now, if I asked you to do this algebraically, you could do that, right? Put 0 into h of t. Equals negative 16t squared plus 80t. 16t squared equals 80t. Divide by t, divide by 16, and you end up with t equals 5. If we keep the initial velocity unchanged, it should not be there, what height would the object have to be launched from to keep it in the air 7 seconds? How would this change the original equation? So this is what it's doing now. And what we want to know is how high do we have to have it so it's in the air 7 seconds. That's what we want to do. So this number is a question mark. So to do this, what I can do is I can put 7 into those t's. What this equals is negative 224 feet. So this point way down here, bloop, is 7, negative 224. So I have to add 224 to my equation. So h of t equals negative 16t squared plus 80t plus 224. That wraps up 2.1 day 1. Let me know if you have any questions.